Hi everyone and welcome to this lecture. Today we are going to continue our discussion on improper integrals. So before I go on and show you an example, we're going to discuss two useful tools that will come in handy, as you will see. And one of them is written over here and it's a theorem. Obviously we are not going to show the proof and we will accept this without any proof. So if you recall that we were considering functions that had the form of p by q, that had the form of rational functions. So I'm calling it a useful tool to calculate the residues. Why? You will understand when I see you when I show you the example. So if you have two functions p and q and they are analytic at a point z0, then if p of z0 is not equals to 0 and q of z0 equals to 0 and q prime, that means the first derivative of q with respect to z, and it is evaluated at point z0, this is not equals to 0, then the residue is simply just p of z0 divided by q prime of z0. So this idea will come in handy, and again we are accepting this without any proof. And a second tool is something you already know from your calculus courses, but I thought it would be a good idea to give you guys a reminder, and that is about even and odd functions. So if a function f of x, let's say you have some function f of x and you now replace x with minus x. If the function remains the same, that is there is no change of sign and all that, then that is called a even function. For example, cosine of x is a even function, and an odd function is such a function that if you replace the x with minus x, the whole function itself picks up a minus sign. For example, sine of x, if you put minus x instead of x, you know that sine minus theta is equals to minus sine theta, right? So that's an example of a odd function. And using these two ideas, one can show that if you have an even function, let's call it g of x, and you want to integrate it from 0 to infinity, this will be simply related with the integral that goes from minus infinity to plus infinity. However, there will be a 1/2 in front. So this idea will also be helpful in today's example. So combining these two ideas, we will see that we can make much longer calculations into a very compact form. So let's try to see the example right now. So today we're going to consider an example, and this says an integral from 0 to infinity. If you recall that we only considered minus infinity to plus infinity in the last video, but today we're going to see an integral that is an improper integral that ranges from 0 to infinity, not minus infinity to plus infinity. And this will be simply x square, oops, I shouldn't write d over here, and the denominator is x to the power 6 plus 1 dx. We ask how we can do this integral. Again, you can see that the function over here, this is an even function, because if you replace x with minus x, nothing changes, right? So what we're going to do is that since this is an even function, we're going to write this 0 to infinity x square x to the power 6 plus 1 dx is equals to 1/2 of this integral that ranges from minus infinity to plus infinity, x square x to the power 6 plus 1 dx. So ultimately this will just imply that minus infinity to plus infinity x square x to the power 6 plus 1 dx is equals to 2 times the integral of 0 to infinity x square by x to the power 6 plus 1. Why I want to go to minus infinity to plus infinity from 0 to infinity range, you might ask, because in our past video we saw that if you have a minus infinity to plus infinity range, there is a nice semicircular contour on the upper half plane. So that's the idea over here. Obviously there will be functions that are odd functions, or there are functions that are neither even nor odd, and we'll see them in the future videos, but this trick over here that I just wrote down will work for any even function. So our goal is to evaluate this minus infinity to plus infinity integral, and then what we'll do, we'll just simply divided by half to get the integral that we originally started with. So let's get started. And again, let me just draw the picture. So this is our plane, and obviously we want a semicircular contour like this. Yeah, it doesn't look like a semicircle, but it will have to do for now. So the first things first is that since we're okay, let me change the color, not a good color. So first things first is that we're going to write the integral that we're considering, that is x square x to the power 6 plus 1 dx, right? And we're going to promote all the variables to the complex variables. Instead of x, now we'll have z, and we're going to replace this definite integral with the contour integral. So if you do that, this will just be z square z to the power 6 plus 1 dz, right? And again, if you recall from our past video, that is the last one, this is minus r to r. This is the semicircle that is denoted with cr. It has a radius of r, and this actually represents this integral over here. So this guy can be written down in terms of minus r to r integral and the semicircular integral. So let's do that. So this z square z to the power 6 plus 1, this can be broken down into two parts. And since this is the real line, again recall that z was simply x, right? So this will be x square x to the power 6 plus 1 dx. Obviously there should be a dz over here, and this is the cr, where you have this z square z to the power 6 plus 1 dz. I'm not going to write the explicit parameterization, and in fact today we will justify why this cr in this case will also be 0, and at the end of the video we'll state a general theorem so that you can understand how you can easily recognize when this semicircular part, that is this extra piece over here, will go to 0. So after this, obviously you need to take the limit r goes to infinity, but let's do it later. You know from Cauchy's residue theorem that this guy over here, this is simply equals to, that is z square z to the power 6 plus 1 dz is equals to 2 pi I and sum of the residues. Obviously I'm not writing the index in the summation, but you understand, because you have to first find out the singularities or the poles, and then you have to calculate the residues, and you need to sum them to get the whole result. So first thing to get the residues you need to do is that you need to put z to the power 6 plus 1 equals to 0. That's how we find our singularities, right? And if you recall, this is just a root finding problem. Again, z to the power 6 equals to minus 1, and if you do the calculation, let's call our roots as ck. So these are our roots, and this will just be the exponential of pi by 6 over here, and there will be a multiplicity term that you guys already know from your complex algebra thing, that this is just, obviously there's the I, so let me write the I down first, and then there is 2 pi k divided by 6, and there will also be an I over here, so let me write it down over here. So these are the roots, right? Now since we are considering the upper half plane, you need to find out which roots lie in the upper half plane, and the way to do it is just to see the angle or the y component, whatever you like it to do. That is, since this is a 6th order equation or a 6th order polynomial, it should have 6 roots, and they should correspond to k equals to 0, 1, 2, 3, 4, 5, right? And if you do the calculation, you will see that only C0, C1 and C2, these three lie on the upper half plane. So there will be 3 points on the upper half plane, and if you do the calculation for k equals to 0, k equals to 1 and k equals to 2, you will find that C0 is simply e to the power I pi by 6, C1 is just I, and C2 is just e to the power 5 pi I by 6. We only need residues for these three poles or these three singularities. Okay, so now we want to calculate the residue. If you recall that if you use the formula that we showed in our past video to calculate residues, you can obviously understand that you have to find all the roots, that is not only just this C0, C1 and C2 but C3, C4 and C5 as well. You need to factor them out, you need to divide them and blah blah blah. But the idea that I wrote down in the first place, or the idea number 1 over here, this idea will help us to avoid that massacre or avoid that amount of lengthy calculation. So since for all these points, you can check it for yourself, I'm not going to do it because that will make the video very long. So for all these points, this C0, C1 and C2, all the conditions that you see over here, that is P of Z naught is not equals to 0, Q of Z is equals to 0 and all these conditions are true. And here this P will be Z square and this Q will be Z to the power 6 plus 1. So that is something you should check, but I'm not going to do it because it's just plugging in the values and calculating. So now let's just follow that idea. So obviously let's write down our P. If you compare our function over here, this one, with the idea that we wrote down over here, our P will just be Z square. So P of Z is simply Z square. So obviously let me write down, now we use idea 1. And Q of Z will be Z to the power 6 plus 1. Alright. So what is Q prime of Z? It's pretty easy. It's just 6 Z to the power 5. Sorry, I wrote 65 instead. It should be 6 Z to the power 5. Right? And we want to calculate residues for C0, C1 and C2. So first let's calculate residue for C0, which is equals to e to the power I pi by 6, right? So what was our idea 1? That the residue at Z is equals to, since C naught, that is the c to the power I pi by 6, this is simply P of e to the power I pi by 6. I'm just plugging in the value for the point that we wrote Z naught earlier, and Q prime, sorry for that, it should be Q prime e to the power I pi by 6, and P was what? Z square, right? So you will have e to the power I pi by 6 whole squared, and here you will have 6 Z to the power 5. That means e to the power I pi by 6 to the power 5. And this is a pretty simple algebra, and if you just do it, this will only yield 1 upon 6i. Similarly, what you can do for the other points, that is residue for C1, which is equals to I, C1 equals to I, if you calculate it, this will just be minus 1 upon 6i. I'm not showing the details. It's similar to just the residue we calculated here above. And then you have to calculate the residue for C2, that is equals to e to the power I 5 pi by 6. If you do it, this will again be a 6i. So all these calculations you can do it for yourself using steps from or following the method of this calculation. And so now what we need to do, we need to find the summation of the residues. So we need to do the sum of the residues, that will include residue of C0, that is at point C0, residue of at point C1, and residue at point C2, right? So this is pretty straightforward thing. You just plug in the values, and this is just 1 upon 6i. Alright, And finally you will write z squared z to the power 6 plus 1 dz, which you wrote as 2 pi I sum over the residues. Since sum over the residues is just 1 upon 6i, you use that result times 1 upon 6i. This I cancels out. This 2 cancels this 6 and gives us a 3. So this is just pi by 3, right? And obviously this thing was broken down into two parts. If you just if I just go a bit above that, see, this thing over here was broken down into this minus r to r thing and this cr thing. So from here we can write that from minus r to r, and you will have a x square x to the power 6 plus 1 dx plus cr z square dz z to the power 6 plus 1 is equals to pi by 3. Okay, so far so good. And now we want to take the limit r goes to infinity. So taking, okay, let's call it equation number 4. So taking limit r goes to infinity on 4, this gives us minus infinity to infinity. Obviously I'm just directly writing it down. This is x square x to the power 6 plus 1, and there you will have a limit r goes to infinity. This is cr, this is z square z to the power 6 plus 1 dz, and since on the right hand side there is a constant, the limit won't have any effect. So this is just pi by 3, right? And we are almost there, but we need to do something about this extra piece. This extra piece over here. So now I'm going to use another theorem, which is probably known as the maximum modulus principle. Obviously I'm not going to show you the proof, and the thing that I want to show you is that when r goes to infinity, this part actually goes to 0. That is, this extra piece will go to 0. So now we use another tool. This is our tool number 3. This tool says that if you have a contour integral or any kind of integral like this, f of z del z, and on that contour, since we are considering the contour integral, if you take the modulus of this whole thing, this is equal or less than some m and the path length. This m is the maximum value for this function can have on that contour, and this dz is actually getting integrated out. That means you are summing over the whole path, and this is turning out to be L. This L is called the path length. So let me write these terms first, and then I will try to show graphically what I mean. So this L is known as the path length, and this M is some maximum value. On that contour. So our contour was something like this, right? It was a semicircle. Let me use another color to just to highlight these things. Okay, this was our contour, and it had a radius of r, a semicircle with radius r, right? So let's say on this contour the maximum value that can occur to the function is m, and this L is just the length of this semicircular arc, this arc over here. So L will be simply pi times r. Now we need to find what is this m. To find m, what we can do is that we can naively break down this modulus thing. Is that we can write it as f of z modulus and this integration of dz, like this. This is a very naive breakdown of this whole thing, and this turns out to be m, and this turns out to be L. So what you need to do right now is that you need to take the complex valued function, that is z square divided by z to the power 6 plus 1, and you need to find the modulus of this. So this z is parameterized on the semicircle, right? So z can be written as r e to the power I theta, right, for any complex number. So modulus of z is simply r, right? That is the thing we expect, because modulus is just a distance. So all these are clear, but now we need to find this thing, modulus of f of z. So you need to write this thing over here, modulus of f of z, and f of z was z square divided by z to the power 6 plus 1, and then you can break it down as modulus of z square, modulus of z to the power 6 plus 1, and modulus of z square is pretty simple. This is just mod of z whole squared, and this is just r squared, right? This part is simple. However, there is a subtlety when you try to evaluate the modulus of z to the power 6 plus 1. Why? This will actually turn out, you expect the result to be, let's say, r to the power 6 plus 1, but this is not the case, right? This is not the case, because if you recall, so let me just cut these things out. So first I need you to recall from complex algebra, complex number algebra, you saw a property of the modulus, that modulus of a plus b, or let's say modulus of z1 plus z2, this is equal or greater than modulus of then another modulus of z1 minus z2. This formula will come into play when you try to evaluate this modulus of z to the power 6 plus 1. So let me show you how. So instead of z1, now you have to write this z to the power 6 plus 1, right? And this is related with this inequality. So this is simply modulus of yeah, it sounds very weird, but modulus of z to the power 6 minus modulus of 1. And if you use this thing again, I'm giving a dot dot to indicate that this is the same thing. So this will be modulus of z to the power 6 minus 1, then modulus of this thing is equal or greater than, since modulus of z is just r, so this will be r to the power 6 minus 1. Now we are almost there, we are almost done building our function. So here finally you have z to the power 6 plus 1, this whole thing's modulus is equal or greater than modulus of r to the power 6 minus 1, which is equals to simply r to the power 6 minus 1, right? So now what you can do, you can take inverse of both sides. That is, if you write this z to the power 6 plus 1, which is greater or equal than r to the power 6 minus 1, you take the inverse of it, or so to say 1 upon this thing, then this is just z to the power 6 plus 1, this should be less equal than, and this is r to the power 6 minus 1, right? And to get the function that we were originally dealing with, that is z to the power z squared divided by z to the power 6 plus 1, all you need to do right now, you have that z to the power 6 plus 1, you just need to multiply with the modulus of z squared, right? So multiply by modulus of z squared and you will have this thing, right? But modulus of z squared was what? R squared. So in the next line you can write it as z squared, z to the power 6 plus 1 less equal than r squared, r to the power 6 minus 1. So this whole thing, this integration of z square on CR, and obviously this limit r goes to 0, sorry, r goes to infinity, z to the power 6 plus 1 dz, this boils down to the fact that we have to take a limit, r goes to infinity, and instead of the function you have to now write this r square, r to the power 6 minus 1, this thing, and then there is this pi r that is coming from the length of the semicircle. And why this line is true? Because earlier we showed that this tool 3 is true and we accepted it without any proof. So this tool 3 is just written just got written explicitly over here. So now you need to just evaluate the limit and see whether this goes to 0. If this is 0, then congratulations, you successfully evaluated it. And if this is not 0, then the semicircular part will also have some contribution in the integral itself. So let's now just evaluate the limit. R goes to infinity. You will have this r square, r to the power 6 minus 1, and there is this pi, and then there is this r. So this is just limit r goes to infinity, r cube pi r to the power 6 minus 1, and if you evaluate it, this is just 0. You know how to evaluate limits. So this result over here says that the extra piece we got over here in this line, this is actually 0. So finally we can say that this guy, that is integration of minus infinity to plus infinity of x square divided by x to the power 6 plus 1, obviously I forgot to write down this dx, this integral is actually equals to pi by 3. So we finally have this result, x square x to the power 6 plus 1 is actually equals to pi by 3. But the integral we originally considered, the original problem was to find out 0 to infinity of x square x to the power 6 plus 1, right? dx. And we also saw, using the idea of even and odd functions, that if you, since this is a even function and you are calculating this guy over here, this is the one we calculated from minus infinity to plus infinity, to get the real result, that is the integration of 0 to infinity of x square divided by x to the power 6 plus 1, all you need to do is that you need to get the result of this guy and you need to divide it by 2, right? So we got the result of this guy, and this was just, the original problem was just 1/2 of the result that is coming from this minus infinity to plus infinity integral. So let me write that again, and finally we put down the result over here onto here. So this will be just 1/2 times pi by 3, and this is just pi by 6. So finally you can write down the result as x square x to the power 6 plus 1 is equals to pi by 6. Pretty nice looking result. Yeah, pretty nice. So now now before finishing off the video, I'm going to make a comment, is that how do you know that this extra piece that you have over this semicircular arc, whenever you have this even function thing, that will go to 0, right? Because you can see that that's quite a long calculation. To do a simple integral, we have to do it in step by step, and most of the time we have to keep track, and things might get nasty, really nasty, if the function is not very nice. So there is a general theorem. So let me finish this lecture off by using a theorem. Again, this theorem is going without proof. So let's say you have something like this, p of z cubed by z, and you are considering some integration that involves this p of z divided by q of z dz, right? And let's say the integration contour is something like this. There is a semicircular, okay, let me use another color. So let's say this is the contour that we are considering, and we want to know whether from this CR, that is the semicircular arc, this contribution is going to 0 or not. So the general theorem says that, okay, so let me use this green color. So this is a general theorem. If the degree of QZ is greater than 2 than the degree of P, then the contribution coming from the semicircular arc will always be 0. So if the let's say the degree of q is, let's say, n, because let's say this is a n degree polynomial, because every function can be expanded in terms of polynomials. So the degree of qz, let's say, equals to n. The degree of p of z is equals to, let's say, m. If this n, that is the degree of n, is greater than 2 plus, or let's, okay, so how to write it? Just let me just write the mathematical term. So if this n is greater than just m plus 2, if this condition is satisfied, then the contribution from the semicircular arc will always be 0. That is, if you write it like this, the contour integral, you are breaking it down, so I'm not using the full formality over here, so excuse me for that. Okay, this doesn't look like x, but it's actually an x. So this is our CR, that is the part that is coming from the semicircular arc of PZ, QZ, DZ, and this was equals to what? This P of Z, Q of Z, DZ. So if this condition is true, where n is the degree of Q and m is the degree of P, then the theorem is saying that this part over here will always be 0 when r goes to infinity, because that's what we do, right, to get the minus infinity to plus infinity integrals. So yeah, these techniques will help you to calculate these improper integrals in a very organized manner. However, you need to just keep track of the numbers, because sometimes it might get very lengthy. So this will be it for today, and I'll see you guys on the next lecture. Thank you.